and I'm screen taping. Okay, and I'm also I will start sharing my screen now so we can follow what am I doing here. How are you doing?
Doing well. Yeah, exams are coming up.
Good. Yeah, I canceled a class today. Got sick. I was beginning a class. I start coughing and I couldn't stop. So I almost canceled this meeting, but I said, okay, at least let me take this going with the students, and then perhaps we can close up. But can you see the routine here?
Yeah.
Okay. Basically, this is yeah. I did this routine in 98, and I just start to work to make an adaptation to the standard we have here, the template star, because when we compare um, any data of tutorial stars, we compare with the standard. Hey, Shaunak, how are you doing?
Hi there.
Good, good, good. So I'm taping this so that both of you can have a copy of it. I sent to you a routine called Veil.pro, and I would like to explain exactly what it does. So this routine I use to calculate the veiling on these low resolution data. And the veiling is the following thing. So you have a star. The photosphere of the star produce very nice absorption lines, quiet, and technically they don't change over time. So you observe now, you observe next year or 2 years from now, they are basically the same because they depend on average surface temperature, depends on some atomic parameters, and these quantities are not supposed to change much. Certain lines change, in part because of the magnetic activity of the star. But those lines and transitions are very specific, and we are not working with them. So when you have some excess of emission from some other region, so you have to combine those two data into one because that's what you observe. You observe emission that comes from the photosphere, all these nice absorption lines, but you also observe some um, excess continuum, which means a flux that has a kind of a flat distribution. And sometimes you also observe emission features that comes from either outflow or inflow, and you have to add those to the combined spectra you observe. So basically, when you observe, you have all these different features from different regions all combined in one thing. And then your job as a scientist is to disentangle all of that and make sense and try to explain how they were formed. So this excess continuum, and perhaps we should meet one day and just go over the physics of it. It is thought, and so far hasn't been changed. It was true in the 90s as it is now. This excess continuum is supposed to be formed when the gas that circled the star falls on the star itself. And when it does, it decelerates. It's a big collision, and then you have deceleration of that gas. So the temperature supposedly goes to 1,000,000 degrees in this shock region, which you don't see it. But um, some of that energy is spread out through the photosphere, creating hotspots, so major hotspots. And these hotspots produce some excess of continuum, right? Some emission that is pretty much flat. It might produce some lines too. I don't know if anybody did any theory of that after I retired in 2000, but in 2000 we all assumed just a continuum. Okay. Um, if you think, let me get a pad here so I can write on. Just a second. I can do it here. So when you have this export, create comment. Where do I add? I want to be able to write. Can I write with this? No. What is my annotation? It's comment? No. Maybe it is. Ah, there you go. Okay. So let's say you have a photospheric line that's something like this. And just for now, let's pretend we normalize this to 1. And just to make it a simple thing, this is 1, this is 0, so 0, 1, and this, let's put it 0.5. So you have a line that has a depth 0.5. So let's say in addition to that, you have a, in fact, this line, if you think, right here. So you have a flux distribution that is something crazy, right? Like you have in your spectra, and then your line is over there, right? Something like this. And this flux has a very small value. It's, I don't know, 6.0, 10 to minus 13 ergs per centimeter square per second. So it's a small quantity of radiation because stars are faint. So imagine that in addition to this nice photosphere, and here you normalize. So basically you take this continuum and then you divide by a line. And then as a result, you have this, which improves visualization, basically. We call this process normalization. So imagine in addition to that, you have some shock region. So we have the star has the photosphere, but somewhere here, you have this hot spot, right? And this hot spot produces some flat emission, which you must add to provide what you observe, which would be your flux plus your line like this. So basically, if this is 6, 10 to minus 13, and you add a flux that is 7, 10 to minus 13, you would have something that is at the order of 13 times 10 to minus 13. Are you following me here? So you take this flux and you add it to another flux, and you have to add those two. And then what we do that in normalized. Okay. So in other words, imagine if you have the star with this absorption line that is, just to make a number, 6 times 10 to negative 13. And you add a continuum. And by the way, is half of it means this depression here, the center of your absorption is at 10 times 3 times 10 to minus 13, which is half, right? So when we normalize this flux and divide everybody by 6, so if we divide everybody by 6 times 10 to minus 13, then I'm going to have my 1 here, and I will have my 0.5 right here. Are you following me here?
Yeah.
Okay. So imagine that this is what we have in the photosphere, but also I add a excess emission That is a heck of a number. Let's say 12 times 10 to minus 13. That comes from this region over here, this hotspot. Got it? So which means when you add those two quantities, now you have something that comes out of the star environmental system that is, now you have a continuum that is what? 18, right? 18 times 10 to minus 13 because we add 12 to 6. Now I have 18. And now I'm adding 12 to 3. My center line becomes now 15 times 10 to minus 13. Does that make sense? So you're just adding a flat quantity to both the continuum and the center line. And this quantity is added, in fact, to the entire profile. But you ended up with the 18 and 15. When you normalize, when you do your data reduction and everything, you normalize. So you normalize dividing not by 6, as we did previously, but dividing by 18 times 10 to minus 13, right? Which means your continuum becomes 1 again. But see what happened. your line center now is shallower because it's going to be the result of what? 15 divided by 18. And this is what? I don't know. Calculate that thing. But it's
0.8-ish.
0.8-ish?
Yeah.
So 0.8, so it was a 0.5 at a 0.8 in a scale that goes to 1, so your line is shallower. Does that make sense?
Mm-hmm.
Yeah.
So this is called veiling, which is a term that people imported from old photographic plates. When they developed photograph plates, if you turn on the light in the middle of development, everything got veiled. So you washed out everything, right? So what we need to do is say, hey, what is this? What is the value of this excess of emission that was added to my photosphere star or my photosphere spectra that yield this veiled spectra? So how do we do that? We have to de-entangle those two factors, and what do? We we compare the spectra of your pre-main sequence with the spectra of a standard. So the standard will show the profile as it should be. And then what do, you add a quantity to this profile and see which quantity should be added to give this shallower profile. And this excess of emission that you are adding is called veiling. And this quantity, you save it. So basically, when you do this for several lines and in your low resolution data, you don't have a lot of lines. But if you go to Ferris data, you have to deal with thousands of lines, basically. And what I did was to reduce the task and go to the atlas that I sent to you guys, the solar atlas, and look and identify some lines that are photospheric lines in the sun, and see these lines in the Ferris data, and then create a table, and then do this task of locating the line, doing the adding of a quantity, find what the quantity should be, and have the software doing this automatically. Um, so that's how we did. So with this heavy high resolution data, we did automatically. We just got hundreds of lines, thousands maybe, and then we let the software take care of it, and then we took an average, and it works fine. But with the low resolution data, we were a little bit more careful because we didn't have a lot of lines. And some of the lines that you have in the low resolution data, you have to be careful because they are lines from our own atmosphere, and you have to not include those. because our atmosphere we don't care for. Okay. Are we all?
So just
Yeah.
Just to recap, so first we have the normalized emission photospheric emission spectra, right?
Yeah, that's how we have, like in Ferrous, that's what we got.
And then to find the veiling, we're adding the additional emission spectra from where exactly?
You have to determine.
Oh, okay.
You have to say, okay, so I have this photospheric line here.
Mm-hmm.
How much of a level like this should I add? Is this? So how much should I add so that when I add my computed final profile is exactly this? In other
Okay.
words, you ended up making a chi-square of your model with your observation. And then when you minimize the differences, then you say, okay, my veiling is this quantity here. Uh, when you do this exercise, you have to realize that sometimes there are variability going on in the star itself. Sometimes the data reduction got some glitches, and the line profile is kind of funny. So there are all kind of uncertainties that you have to kind of be aware um, when we publish or we submit our results to some committee or something, which I would like you guys to do it somehow, probably next year. Okay.
So how so I see the first the steep the bigger depression
Oh,
and
this one over here.
how
Yeah.
so how do we determine um the curve on top of it? How
Oh, this curve over here.
yeah.
Okay,
Uh-huh.
this is the T-Tauri star.
Oh, okay, so that's our reference star.
That's your reference star. That's
Okay.
your TW Haya or GQ Lupi or whatever star you have.
Mhm.
So essentially, what the software does, and as far as I remember, that's what I did. I had a table of for the high resolution. I have a table of several lines that I previously have selected as good lines that I would see in my cool star. And then what the software would do is to take this line, find in the T-Tauri star where that line was, find in the standard where that line should be, pretty much in a way similar to the one Dr. Raja showed in his own work. So that's what we do when we compare with standard. And then we bring these two specters together, and then we do little tricks just to eliminate problems. And I would like to show the program, this Veil.pro, to highlight what are these little tricks we do to make sure we can compare the data. So what the software does, and I didn't have a lot of a coding experience, but maybe you guys have. You guys can find a better way to code this. What I simply did was the following. So this is my standard, and 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 here's my tutorial. So I would know veiling. So the veiling, I would create an array that could be 0, so no veiling at all. So the profiles were the same. 0.1 all the way to a heck of a veiling that, that's the most we can get. 5. So with the steps of a 0.1. So then you know what I did. I take my template. So I have template. And then I add 0.1 to that template flux. And then I see the result. And I compare with my T-Tauri star. Is it good? What is the chi-square of it? And then I save the chi-square. And then I go to the next one. And then I do the same thing. And then I compare the chi-square. And then I keep doing the same thing to the point that I have an array of several chi-square. and the veiling that I choose would be the one with the minimal chi-square. So it's stupid. It's a bad coding, and I didn't mention that in the paper, but that's a bad coding. But you know, in a rush, that's what I did. But you guys could find a better way. There are techniques um, that search for missing parameters in a software like that. Instead of making an array and try different attempts to see which one has the minimum square, you have these softwares, this coding that find what is the solution. So try a number to the right, let's say, or pick a number in the middle, go to the right, go to the left, and then use some differential equations to figure out in which way to go, and then quickly find a solution. In my case, I have a lot of computer coding going on, but since time was not an issue for me, that's how I did. Okay. Okay, so let me show quickly how this code goes. You could either um, keep in IDL, or you could play with Python or both, and do your own coding. And I really recommend, if you have the time, to do both. If you have the time, if you don't, do the one you are more comfortable now. But here how it goes. So the way I did, this code is set to work on the data that I had for GQ loopi. And the extension that I have here is not veil, or it's not SAV, but is an extension DSK. And here's my problem. This DSK extension is the result of an application developed in Berkeley, which is very convenient, and that was developed by Jeff Valenti. He's in space telescope now, and so what it does, you have you are calculating things in the middle of an application, and then what you do, you want to save, let's say, an array of wavelength, and then you want to save a string with information, and you want to save in the middle of your code, you want to save something else. And then what this R disk does, which is read disk, and there is another function that works like that one called W disk, which is write disk. So what they do, they read all these different strings and variables that you saved during calculation, and so it write it down, and you can read later, and put in an orderly way that doesn't matter if you are saving binary or if you are saving ASCII files. No matter which format you save, you can read later in that order, and then you know the parameters, what should it be. So the first file saved is parameter 1, the second file or string saved is parameter 2. So when you want to recoup one of these files, you know which one you should read. So we could change that. We could do in a different way just to read the SAV files you guys have, right? So this is something that must be changed. But basically, what the program does, it locates the T-Tori star file, right? The spectra with it, like we did, a few weeks ago. Locate your template, your standard, which for the stars we are going to work is going to be K5, K7, or M0. If we don't have, we should download, and I have to find them. And I don't have in my computer, and you don't have either. I have the records, but I don't have the standard file. So basically here, no, let's go to the video right here. I did this program to create veiling for a bunch of stars at the same time. So I had the students, and they would do this work, all day long. It's kind of a tedious, if you will, but it gives good result at least. Uh, so so basically, the FN is the name of all the stars with their respective tree address. In my case, I was playing with it, and I already changed it to find them in the folder that I had locate them. This command here, what it does is just open the place in the disk where information about the veiling is going to be saved, so that later on we could read it and do analysis basically. But this is just opening up a space where the computed veiling is going to be calculated. So here it's reading the T-Tauri star, and the wavelength was stored in the record number 4. That's how I did. I reduced the data and I saved it wavelength in the record number 4, and I saved the flux, the absolute flux calculated in the record number 7. So basically here it's reading wavelength and flux. Now with the restore files or restore application we used previously, we don't need that. With the save file, you just restore and you have wavelength and you have flux automatically, so you don't need that. So this must be changed. The next thing I did was the following. Degrading the T-Tauri star to a resolution of 4. Why did I do that? I did that, which we don't need to do for the files we are working, because these GQ Lupi, these stars were observed with a very bad resolution, and I had to downgrade the spectra to accommodate and to visualize those stars. Like Furious data has a heck of a resolution. It's 0.2 angstrom, 0.2. The T-Tauri star, the low resolution, it is 1 angstrom, if I'm not mistaken, 1 or 2 angstroms. And the one in GQ that I was working with a student had a resolution of 2 or 4, and I had to degrade the spectra so I could measure veiling. So we will not need to do that. We can bypass this downgrading aspect of the code. So we have to redo that. We have to do some different changes in here. Now this comes with the first tricky thing. You are going to compare the T-Tauri star with the standard, and so what your visual inspection will do, or your software will do, is to do this comparison, assuming that the scale in wavelength is the same. So these steps here, and I'm taping these so you guys can go back there later and review this. What these steps here do is to take the wavelength scale, rebuild the wavelength scale, and the way we rebuild this is you take the separation between 2 pixels in the middle of your spectra. So let's say you go to the middle of the spectra and then you take 2 pixels, what is the wavelength of one and the other, and take the difference. So the difference is going to be a double-digit real number, and then what you do, you take that difference and you add to the first pixel, creating therefore a scale that is equidistant. Because these wavelengths are not equidistant. The way the data reduction goes, they can be anything. And when you reduce 2 different datas on different days, the scale is all different. So what I'm doing here is to make it uniform. So you take the T-Tori star, the standard, and make the scale uniform. And that's what is being done here. So this NW new wavelength is a new scale. And then once we create this new scale, this function here, what it does is to interpolate. We take the old, right, spectra and wavelength, and then interpolate with this new scale NW, and then we have an interpolated spectra. So basically, you have your profile, and you have a wavelength associated with that profile. So you interpolate into the new scale. You still have the same profile because the separation and the resolution is not that bad. So you're not inventing points in between. You still have the same profile, but it's uniform now. So the wavelength scale, both for T-Tori and standard, are the same, and that's how we get to this point in the coding. The next part is to do the veiling itself. And the way the veiling is being done, I select windows of 50 angstroms. So this spectra goes, I don't remember, perhaps from 3,300 all the way to 5,000. So you take windows of 50 angstroms, and then in that window you spec for absorption lines. And that's what basically is being done. You are taking steps, and in this case, see this clicking thing here. When everything is being visualized, so you like in let's say if your spectra is something like this, right? You have some crazy thing. And you want to normalize this. You want to bring the spectra to a normalization 1. So what I found it works quite well is just to come with one dot here. You click another dot there, and a third one there, and a fourth one there. And then automatically the software will pass a line through these points and divide your spectra by that line, and therefore normalizing. So the main result is you're going to have everything nicely normalized, and then you can do the same with your standard, the same with T-Tori, and then you can go to the process of calculating veiling, doing this bad coding that I invented, and maybe you guys can do something better than I did. And pretty much that's it. So here's what I recommend you guys to do. If you guys could open up this code and adapt it to the data we have, my job is going to be to send you the template, the standard, over the weekend, and you have to change the reading and the storing information. Instead of using redisk and wdisk, to use the save and restore functions, because it's going to make it faster and more kind of a it's going to be easier to deal than try to understand this other function, which we can do one thing at a time. Any question? Is all good? Okay. And you know the priority, right? The priority is to get good grades. If you have free time, instead of playing video game, which is good, you guys can do some coding and see where you go. All right?
Yeah, I'd be interested in seeing if maybe we can transfer this to Python.
Yes, I definitely recommend that. Dr. Raja recommend that too. My daughter keeps saying that I'm a dinosaur with IDL, but my brain, to change the patterns and pathways, it's not easy, especially because I'm not doing this full time. I'm doing this as I drive back home, basically. Yeah, but you should do. You should do. And if you can code both ways with IDL and Python, it's even better.
So right now, pretty much the issue is that it's still using the DSK
Yes.
file format.
Yes, and the files are in that format, but we don't need it. We can use restore, we can use save to save the data. And by the way, all these steps here, what I recommend you to do is to do outside a program. You do as standalone in your command line. That's either in Python or IDL. Like if you're looking at my computer here, so I could take, for instance, steps and say, okay, I have a file name. So create a file name, tts equal, and then you call the file name that is stored in your disk, whatever that is, dot save, right? Dot save, and then you do template or standard is equal whatever name that is, and then you work with this file. So you bypass the program. At least you have some sense of what the code is supposed to be. So when you have a sense of what the code is supposed to be and what the science you are going to achieve, then you can structure all of that in a code that is going to have your mark, pretty much your hand and your skills. And then you can share. Don't show to your dad. Otherwise, he's going to try to do it for you. He has to be out of the loop. I don't think he's listening to us yet.
No, I think he's in the call, but may not have heard anything yet.
He's not laughing.
Mm-hmm.
All right. Okay. Very good. Very good. I saw Rick is there. And hey, Rick. Terrence. Hey, Terrence. Can you hear us? Terrence? Terrence is an evergreen professor in the field of biology, and he does a lot of independent work. And I heard a lot about his efforts to bring native plants to evergreen grounds. And he did a workshop, and I set myself to go. Something happened. I think I had a family trip or so, and I couldn't be there. It was on a Saturday. And he's very much interested in what we do, and perhaps he could initiate something in the field of biology. So he's just checking out, but I can't hear him. Philip, Ognian, can you hear? Now you can hear. Okay, very good. You are not in the car, huh?
No, not in the car. I mean, last time it was had to stay a little bit longer at work.
Okay, all right. Any floor discussion going on? Lee Rottler is not gonna come. He might check out later. He said, but he's not around. I have one, and that is. Let me see if I can pull up here. So this is the final flyer of Natasha talk, and I had two other graduate students. In fact, one is a postdoc. No, the two are graduate students. Natasha is a postdoc. They are going to send me the the team and their pictures, and I will have it. But what I would like to share with you is that Vera Nazarov, which is our secretary, she is very good in giving a professional touch to the flyer, and hopefully this is going to be done. But that's what we have so far. This was done by Olenka and me, and I think she's gonna work now and make it more permanent. So the only thing we are going to change maybe this picture here, and of course what the person is talking. Probably this is too much information, but that's what I had, and I didn't have time to improve it. Um, and this is an online talk reserved to the first 100 attendees, the date, um, and the address. So basically, that's it. Any on that? So we start in June, not in May, because May is too soon. So then we have June, July, August, and then we have to start populating the fall. And I see if you guys have ideas and suggestions, just send it to me, and then I can contact these people. I mean, the idea is to have graduate students or postdoc giving talks about their research. So basically, their research is going to be in the news, I don't know, 2 years from now, 3 years from now. So we are kind of ahead of the game, I would say, especially for the high school crowd that is coming here. Is important to see what's going on.
The lectures, it should be, let's say, can one postdoc or graduate student hold one or more than one lecture, or basically everybody will be assigned one lecture?
It's good to circulate. If they can give more than one, that would be great. To have the offer. Say it again.
I meant because probably some topics may require more than, let's say, 45 minutes or more than.
Well, here's the deal. In general, it is a training to be able to convey technical information in a simple way to the public that is not necessarily an audience of graduate or scientists, so what I'm telling them to do is to condense the main idea in 45 minutes. So I'm pretty sure they can do that. I mean, any scientific topic, you can in a bar. In fact, there is a beer lecture, something like that, and I will start publicizing here, in which they invite exactly top of line scientists to give a talk in a brewery, and the talks are small, 30 minutes or so, and then it's just the main point without going to a lot of the details and the technical aspects of it. That's what I'm looking for, is to be able to convey some deep aspects of their research and give, especially to our students, the the I mean the guts to ask questions, to be able to raise hand and say, hey, can you explain this again? This is very important. It's very important. It creates a culture that puts high tech and advanced science in the hands of our students who are initiating this step. So that's what I'm looking for, basically.
Yeah, that makes sense. Yeah, thank you.
On a side note, yesterday we went to the college council because we submit a request for a spectrometer that was approved in the tech committee, and that was taken to the college council, and they told me to show up there. I was about to back up on the proposal because we have more urgent matters, and that is to hire a lab technician, basically. we don't have a lab technician for astronomy, and this is becoming ridiculous. Um, Especially with the telescope, we have precision instruments and cleaning process. You all know we have the public viewing, and there is not a person in charge of doing the hard work of maintaining. Um, so I went there because they suggest you have to go. We can't back up now. It's kind of ugly if you say, "Hey, I want a spectrometer," and then when they decide to listen to you, say, "I don't want it." So then I went there, and of course they say, "Well, we don't have the money. Don't have $35,000." And then I tried to sell the idea. The spectrometer is not just the spectrometer, but it comes with a camera that can be used for astrophotography and to bundle the STEM projects we are engaged with freshmen initiating their career at Evergreen, especially the guided pathway group and trio from Michael Osorio, the Evergreen Upward Bound group. As a freshman, underrepresented, perfect for what we want to do. So I try to sell the idea of astrophotography, which is something we want to do and is part of what we intend to do in the next 2 years. Um, so the president said he was going to give food and he was going to talk to the foundation and see if the foundation can find a donor that can pitch some money towards the project and perhaps do some fundraising in the observatory. So that's where we are. So we do. It was nice to see that what you guys are doing in the observatory, especially Rick, um, is pretty much in the eyes of the president. He likes the idea. He likes the public outreach, and so that was good to hear. And let's see where we go with this public, passing the bag of benevolence and try to get some money to buy the instruments. A spectrometer would be good, by the way.
Is the spectrometer going to be shared for physics WAPs, or it is?
I don't think physics needs. Physics doesn't need. I mean, physics has a lot of spectrometer. We have 15 spectrometer for physics, and that is perfect. It's low sensitivity. It can get discharge tubes, and that's what it's good for. But it cannot see stars. Rick has tried hard to put in a telescope and get some signal. It doesn't. I mean, we can see the sun. The sun is nice. The sun, it works. We can see H alpha. We can see sodium lines, solar sodium lines. We can see the H and K calcium too, which is exciting. Um, but that's it. All right. So, any more subject? All good?
Yep. So I've been trying with playing experimenting with AstroPi, and
Yes.
look that AstroPi has, for example, very interesting additions to the library, being able to transform one coordinates to another coordinates, galactical coordinates, and so on and so on. Transformation from parsecs, let's say, to light years, all that from for the flux, from joule per square meter, per blah blah, all to watts. All that transformations are built in. The most important thing for us, this is the tools for fit files, for different formats for the fit files. There is enough documentation how the fit files are built. There are tables and headers and so on and so on. And AstroPi has all that capabilities to play, to take the image, to put the image together. We can ourselves generate fit files. We can use the fit files to generate different pictures, images, to put everything in in arrays and
Wonderful.
different data structure. So that's pretty. I mean, it is this stuff which usually has to be done per hand. For example, from one coordinate system to compute in another coordinate system, AstroPy offers all that stuff. The most important thing is the background of the visualization, where the data is put, and for visualization itself, usually I also looked at the Raja stuff. There is a float-lib library with which we can create whatever we want graphics. These nice graphics what Raja was showing in his presentation, all that is done with this set of tools which are nothing extraordinary. I mean, Raja was showing how to put well-known libraries together to create very good graphics, very good presentation. So
that is impressive. That Jupyter, what that Jupyter does. So in the middle of the coding, it creates the graphic. It generates the graphic there, and you see the graphic being generated. It's just amazing. It's just really amazing.
And the very nice thing is, for example, with Jupyter, documentation and execution goes at one place, and it looks. It is very convenient to add new stuff, to execute that stuff, and to put it together. It is. I think this is the right. Put it that way. AstroPy are the ideal thing for citizen science because it does not require installation of some kind of fancy integrated development environments. No Eclipse, no IntelliJ, no something weird, no command line. It is just very nice and very forgiving user interface.
Talking about those tutorials, Shaunak was looking for the links to the tutorials that Raja gave us. Would you happen to have it? I couldn't find it in my computer.
I think Phil has them. Phil, you found them, right?
You mean what kind of tutorial?
Raja, he said he had a tutorial that he gives to his graduate students, and he would be willing to talk about it to us, and that's what he did. And he sent the links, but I can't find that email. And I remember that Onion, right after I sent it, he said, "Oh, those are fantastic! It's very good."
Yeah, I should have them.
You should have it.
Yeah.
And I tried to find it for Shaunak and I couldn't. So if you find it, can you send that link to Shaunak, please?
Of course, yeah. Another thing, I think you found Professor Raja's website in.
Yeah, I'm looking for that right now. Actually,
yeah,
I had it at one point. I'll get back to you when I find it. It's in like the string of emails somewhere.
Okay.
Yeah, it's available. I will resend the email. No problem at all.
We are already losing information. That's good. That's good. I'm not saying anything, so it's good.
And in terms of what we need to, for example, these tasks with the veiling, with the variable stars, I of course overheard something when you were talking to him.
You were behind the door. Oh, what's going on here?
Of course, I was hiding behind the door. We have.
Here's the plan for both of them. I would like them to, if they have the time, because I know in the summer they might be a little bit more free, but certainly I would like them to be able by November, December, to have something done with Pharaoh's data, and maybe think about submitting some poster presentation to the AAS meeting in the summer, in case they are willing to go, and I think they should. So I think that's a great opportunity. The second thing is there are summer opportunities for them. They should try to embrace, and if they have this research going on, the chances of getting accepted increase a lot.
Of course.
So I don't know if it is in their pathways to try to do this before going to college. But if it is in your agenda, so completing a work, it's a plus that goes in your resume. And if you have a poster accepted, it's even better. And that's what we are shooting for, to be able to get a poster accepted. So for that, we need money, because these kids can't go to a conference without with a horse. In fact, we don't have a horse. They can't go with a bike, so they have to have an airline ticket. You have to pay registration and all of that. Usually, when you are in an institution pay, but you guys are not. So I have to pitch some donation, again, bag of benevolence going on, so that if the opportunity arises and we need to send students out, and since they are not linked to Evergreen officially, if they were, I think the student services could chip some money. But since they are not, we have to make sure we have that money available to send them out to the AAS. I don't know where the AAS is going to be, but it's always in different places.
That is awesome. From our side, what I wanted to say is that from, let's say, from software point of view, everything, most of the tooling, instrumentarium, what we need is there. And fortunately, it is designed so that it is very straightforward to use it. Bottom line, the students don't have to deal with programming. The students have to deal with science.
Mm-hmm.
And I think this is the objective. I mean, because both of them, I think they're computer literate, I mean, programming and so on and so on.
Right.
The focus is to use these tools to do the science, not to do the programming. The objective is to do science.
Right.
Right. And so on and so on.
Right. That's the fun part. We haven't started in science yet, but we will. So hopefully in the summer we'll start seeing data coming in, and that's gonna be exciting.
Yeah, and let's say from our side, I mean the old guys, we can support them, for example, with some kind of software tool is needed, something needs to be investigated, how exactly to be done. That's fine, some kind of script or program, or we can use this shortcut. But the real science, I mean, this is the stuff what the students are gonna do.
Very good, very good. All right, folks. I guess that's it. I was taping this, by the way, and I'm sending this to all of you. But I was taping more for the students because of this coding thing. But yeah, you got it all.